Hello, my name is Pragna and today I'll be presenting a summary of my internship work. So during this internship, I strengthened my basics in digital design, Verilog, CMOS fundamentals, processor architecture concept. Later, I worked on projects like AI-based timing analyzer and complete ASIC design flow for UART IP. One of the initial tasks was implementation and simulation of various digital circuits using Verilog HDL. First, I designed basic logic gates like AND, OR, and XOR. Then I worked on multiplexers, including 2x1 and 4x1 mux, using both data flow and behavioral modeling. Next, I implemented a 4-bit combinational adder and a 4-bit comparator to perform arithmetic and comparison operations. For sequential circuits, I designed a D flip-flop using both blocking and non-blocking assignment. From the waveform analysis, I observed that D flip-flop output changes only at the positive edge of clock, which confirms its edge-triggered behavior and memory property. And blocking assignment executes sequentially and updates immediately, whereas non-blocking assignment executes in parallel and updates at the end of the simulation time. All the simulations were performed using EDA Playground. Next, I had a task that strengthened my CMOS fundamentals. I learned that CMOS technology uses both NMOS and PMOS transistors, where NMOS forms the pull-down network and PMOS forms the pull-up network. This combination provides low power consumption and high noise impunity. I also learned MOSFET operation, that is the three regions of its operations in cutoff, linear, and saturation depending on the gate and drain voltages. The CMOS inverter is the basic building block of digital circuits where the output switches according to the input voltage. And also, I learned about how the performance of CMOS circuit depends on factors like propagation delay and power dissipation, and the effects such as channel length modulation and body effect and its influence on the circuit behavior. I also learned advanced technologies like FinFET and its improved performance and scalability in modern VLSI systems. Then I studied finite state machines, specifically Mealy and Moore models. I learned in that in Mealy machines, the output depends on both current state and the input, making it faster but slightly less stable. In Moore machines, the output depends only on the state, making it more stable but requiring more states. I also studied about Transformer Engine, which is a high performance library developed by NVIDIA for transformer based AI models. It uses FP8 precision to significantly speed up computation while reducing the memory usage. At the same time, it also maintains the model accuracy by dynamically adjusting the precision whenever it is required. This transformer engine developed by NVIDIA is specifically for the NVIDIA Hopper GPUs, which are designed for efficient low power processing. In PyTorch, it works using an autocast, which automatically selects the best precision for different operations. However, one challenge is that the installation is complex because it depends on the compatible GPU hardware and specific software version. Then I studied processor architecture and pipelining concepts. That is about how a processor executes instructions through 5 stages. That is instruction, fetch, decode, execute, memory access, and write back. Pipelining allows multiple instructions to be processed simultaneously, improving the performance. For example, an add instruction performs only register operations, while a load instruction involves memory access. There are two main instruction set architectures: RISC, which uses simple and fast instructions, and CISC, which is more complex instructions. The memory hierarchy ranges from registers, which are fastest, to storage, which is external, which is slowest but cheapest. Finally, in system architecture, the Harvard architecture is more efficient than von Neumann because it allows parallel instruction and data access. Next, I studied different hardware platforms such as FPGA, SOC, and ASIC, about how FPGA is reconfigurable and ideal for prototyping, and SOC integrates CPU, memory, and peripherals into a single chip. And ASIC is designed for a specific purpose and provides the highest performance with low power, but it is not reprogrammable. I also studied UART communication, which transmits data serially without a clock using start and stop bits. Next, I explored AMBA, which is a standard bus architecture used in SOC. It includes AXI and AHB for high performance communication and APB for low power peripherals. AXI supports high bandwidth and parallel read and write operations. A key concept that is the valid ready handshake mechanism, which ensures reliable data transfer. This knowledge is important for efficient SOC integration. Then I was placed in the STA team, and my first project was Python-based AI timing analyzer. So basically, we know that in digital circuits, timing is critical. Signals must arrive on time, otherwise the chip fails. Timing analysis checks whether the data arrives within the required time using the parameter called slack. So slack is the time difference between the required arrival time and the actual arrival time. This tool reads timing reports, detects the negative slack, and provides automated suggestions. To explain the modules in this project, it consists of 4 modules. First, the Parazer module reads the timing reports and extracts the start points, end points, and the slack values using regular expressions. Second is the Analyzer module, identifies timing violation by checking if the slack is negative and generates a summary. Third is the AI Helper module, classifies violations into severe or moderate, and it suggests fixes like pipelining or reducing the fan out. Finally, the CLI module acts as a user interface, displaying the results and analysis in a clear format. And this is the final timing analysis summary that we got. So in conclusion, the project automates timing analysis using a combination of parsing, rule-based AI, and CLI interface, which helps designers quickly identify the timing violations and fix timing issues and improve the productivity, and it reduces the manual effort required from the designer side. The second project was UART IP design from RTL to GDS. In this project, I designed the UART IP and implemented a complete ASIC design flow from RTL to GDS using SkyWater 130 PDK and OpenLane toolchain. So the tools used for this was OpenLane, OpenROAD, Magic, NetGen, and GTK Wave. So in this, we implemented a UART look-back design where received data is directly transmitted, and the design flow included RTL design, synthesis, floor planning, placement, clock tree synthesis, routing, and verification. The design was optimized for 10 nanosecond clock, and the result shows positive timing slack, zero DRC violations, and successful LVS verification. So we generated the final GDS file, completing the full ASIC design flow successfully. So this was the learnings from my internship till now. Thank you.